Okay. Right now, finally, we are getting to the core of our course, I would say, because something that we're most interested in are the discretization methods for engineering problems. So far, we've covered the governing equations and some numerical tricks. But really, right now we are stepping into the topic, and we will be starting with the finite difference method. To be honest, finite difference method. How many of you already know the method? That's good. So that's good that you know. That's bad that I will be reintroducing that, and I don't want to skip the details of the method because I think some concepts and some numerical phenomena can be best explained using the finite difference method. So, for example, the problems with the advection diffusion equation, with stability, the concept of the numerical diffusion that arises in numerical schemes, these are the things that can be, in my opinion, at best shown on the example of the finite difference method. So we will be going not so quickly through the method. I just want to make sure that you really understand the numerical instabilities, the wiggles, the artificial diffusion that arises. I want to make sure that you know how to implement the boundary conditions and how to generate the matrix for the system. If something isn't clear, please stop me immediately. If something's clear, you can give me a sign that it's clear. But I don't want to accelerate anyway. So. Okay, so let's start with surprise. This won't be the Laplace equation. It will be something different. Let's start with the advection diffusion equation, as it represents most of the scalar transport problems. Okay, I've got it right now in my notes. Or maybe let's move to the Laplace equation or Poisson equation. Obviously, if we, for a minute, or not for a minute, maybe for an hour, if we drop the convection term, then we're left with the diffusion equation. And let's, sorry, and let's start with that, just a minute. What we already know is that if we want to discretize such a second derivative, we can do it with the finite difference method that we have partly introduced before break. So we can do it this way. I minus 1 minus 2 is I plus 1 divided by h squared equals fi, and we need to have some boundary value problem that we're going to solve, and our boundary value problem, let's assume, is defined by this equation. We've got the domain that extends from x equals 0 to x equals 1. We need to define the boundary conditions, and let's assume that for our system, u at x equals 0 should equal 5, and we want to have the Neumann condition at x equals 1, and this one should be 0. For a finite difference method, or basically for any discretization method, we first need to introduce the discretization of the domain. So what we do is we introduce the nodes, and we will have, well, finite differences between the nodes. So that's the discretization of space. Again, what the next step is? The next step is to discretize the equations. So we are moving from the partial differential equation. We are moving from the, well, partial, just one variable here. So we are moving from the differential equation to the difference equation. That's the discretization. And obviously we generate how many equations do we generate? Let's assume we've got two different ways. We can either assume that here already the first node on the boundary is 1. This is one of the conventions. The other convention would be, okay, let's assume the first node is the first internal node. Let's start with that one. Then h equals 1 divided by n minus 1. How many equations do we have?
N equations.
Yeah, we can say that. But just see that if you want to really generate equations that are defined by the differential equation, then you can only do it for the internal nodes, because you can't actually, well, first of all, you don't have a neighboring node anywhere here to exploit this formula to write the difference equation at the first node. Like you've got no neighboring node. That's the technical problem. But the motivation is that you need to impose the boundary conditions at the ends of the interval. So we will need to replace them. So let's start with generating the matrix structure. And how do we solve it numerically? Well, we need to generate the matrix times the vector of unknowns. The vector of unknowns would be u1 to un and some right-hand side vector. This row is the first row. This one is the nth row. So as already said, let's start generating equations from the second node, not from the first node. So, well, what happens is we've got minus ni divided by h squared, because this coefficient multiplies ui minus 1. Then if we're assembling the equation for the second node, then what stands in front of ui? This is then plus 2 ni over h squared. And again, something that multiplies ui plus 1, and obviously in the matrix multiplication, this coefficient we multiply. This multiplies u1, this one multiplies u2, and we need to have something that multiplies u3, and it's exactly the same as the coefficient in front of u1. So again, nu divided by h squared. If you take I equals 3, then we're generating the next row in the matrix. Obviously, already our stencil for I equals 3, our stencil is composed of that, and that node. So clearly, there is nothing from node 1 that would contribute to the equation. So we've got 0. This one is shifted. And what you would observe in the matrix structure is that these terms go until you are writing the equation for node n minus 1, because that's the last node for which you can write the equation in its full form. So this one is again 2 ni h square, here minus ni divided by h square, minus ni divided by h square, and we finally arrived at the last nth equation. What can we do to implement the boundary conditions?
We should approximate the derivative at the point x equals 1 and write that numerical scheme into the matrix. And in the point x equals 0, we should just insert 1 into the matrix at the point 1, 1, yes, and zeros to the other elements of that row, and the value 5 to the right-hand side.
Yeah, so let's start with the first equation. What we need to do is we already have an algebraic equation, so there is nothing to discretize. We just need to impose that boundary condition. So basically we need to introduce this equation to the matrix. And we see x at x equals 0, so basically u1 equals 5, and we need to introduce such an equation to our matrix. The easiest thing to do is to say, okay, so u1 equals 5, and everywhere here we've got zeros, and this already satisfies our boundary condition. What we need to do here, as Adam said, we need to discretize that. So what kind of fine difference we can use? We can only use the backward difference. Basically, we would write n minus 1 divided by h equals 0, because we need to fulfill such a Neumann condition. Obviously, we can also write simply that. And this translates to having coefficient equal to 1 here. 1. And here we've got minus 1. It's minus 1 equals 0. What I forgot, just a minute, what I forgot is when discretizing the equation, we need to enter the source values. If we've got just function that would be 0 everywhere, then we've got zeros. If not, then we've got like f at x2, f at x3, etc. Anyway, these are the known values that are well determined because it's just the right-hand side, the source term. Question?
Yeah, well, technically this approach is correct, but I reckon we can do better by using the main equation and extracting u(n+1) and using central differential. We can have a better order.
That's true. So basically what you say is that we can use the equation to generate a hypothetical value that would be here, and use the find difference, central find difference, to generate the equation for that node. That's true. Like if you, because generally, if you would investigate this approximation is the approximation of the second order. So basically, the whole method would be of second order. When I'm doing something like this, applying the find difference of the first order, then I'm actually lowering the order of the method to maybe not fully 1, but something really lower than 2, definitely. Yeah, that's a smart way. I will skip this derivation right now, but it's a smart concept because we come to that during discussing the find volume method, where you will see that very, very often the boundary conditions in find volume method are implemented using the concept of ghost cells. So basically, the cells that do not exist in the mesh, but are artificially added to mimic the presence of the solution on the other side of the boundary.